All right. Well, welcome back to Intro to Physics, whatever day this is. 6. Okay, so here we go. Moving on from whatever that was. Okay, so we've talked a lot about like graphically how to go from position to velocity to
Oh,
acceleration, that sort of thing. We can
Miss
do
Amor,
mathematically as well. Yes,
I had a question about the other side. Can we go back?
yes, we can. This one?
Yes.
Perfect.
Um, you see the line that comes after the flat line on the position diagram, and then like how like compares to the velocity one.
Yes.
Oh wait, you're a little cold. Yeah, that one.
Yep.
On my notebook, I drew it as one big line, like a long line, not the short line that was on the on the velocity graph right there.
So how did you draw it? Is it still like a negative slope?
Oh no, it's not a negative slope. It's just like the velocity graph, but like it was a longer line than that. I think I got confused with the sizes.
Okay. Well, it's tough to know like exactly how to advise you without seeing it. So if you want to stick around and show me your sketch after class, I'd be happy to talk through it with you.
No problem, but it's kind of a crude sketch because I kind of just winged it and I didn't really see some of the lines there.
Mine is a crude sketch on here as well. We do what we can. It's all good.
Yeah.
Okay. So we're not done with graphing. We're just taking a quick break from it and then we'll come back to it. Okay. But so far, like I said, we've been finding velocities and accelerations graphically, but we can also do it using calculus. So calculusly, if that's a thing. So graphically, we use words like slope and sorry, hold on. Give me a quick second. My computer's being dumb. Okay, and we're back. So a comment in the chat. I haven't learned derivatives yet, still in high school. Are we gonna go further into that? Yes, we are. And they're really probably not as bad as you think they might be. So anyway, graphically, when we talk about going to velocities and accelerations, we use words like slope or area under a curve. And in calculus, these are also used, but they have different names. They are called derivatives and integrals. So that's what we're going to be looking at further now. So again, if you haven't taken calculus, this is kind of like a really quick crash course into how to do these things. And then you'll take like an entire semester's worth of this derivatives topic in Calc 1. So this is just a really quick insight into it. But you'll definitely see this a lot. You'll have a lot of practice with this. So the rule that has been kind of mentioned here already is called the power rule. And so when we take a derivative using the power rule, what we do is we multiply the coefficient by an exponent and then subtract 1 from the exponent. So here's what I'm talking about. Okay, remember this symbol out front, d over dt, means the derivative of. So at least that's one way to write it, d over dt. Now this variable in the bottom here tells us what we are finding, basically the slope with respect to, or what we're finding the derivative with respect to. It's kind of our most important variable that we're dealing with. So since it wants us to take a derivative, d for derivative, or actually d for delta because it's a change in, the change in something over the change in time, this t is the variable that we are most interested in. So the derivative of this expression, t to the 5th, with respect to the variable t, here's how we do that. We multiply the coefficient, which in this case is 1, right? 1 times t is the same thing as t. So we're going to just drop in a coefficient of 1 there. Multiply it by the exponent that's on the variable. So here the exponent is 5. So we'll do 5 times the coefficient.
Oh no. Oh,
This day.
you good? Okay.
Ah,
Perhaps use your phone as a hotspot.
it is used as a hotspot.
Oh,
I know,
must be a
right?
bad storm.
Yeah. Okay. Anyway, back to it. Can you guys still see my power rule slide?
Yes, I can.
Okay, and we're recording.
Mhm.
Cool. Here we go. So we've multiplied the coefficient by the exponent 5, and now we subtract 1 from the exponent. So 5 minus 1. So that gives us a final answer of 5t to the 4th. Congratulations, you've just taken a derivative. It's amazing. The power
Can
rule
you do it
is
again?
awesome. Yeah, I think I have another example to show you as well.
Oh no, like can you do the one that you just showed us again? Because you were kind of cutting up and I was trying my best to follow you.
Sure. So for the power rule, we multiply the coefficient by the exponent that's attached to our interesting variable, the one that's expressed to us in the derivative, right? So since we're taking the derivative with respect to t, we care about the exponent that's attached to t, which is 5. Now, since this is just t to the 5th, we can kind of imply a coefficient of 1 because 1 times t is the same thing as t. So the coefficient times the exponent would be 5 times 1. And then we subtract 1 from the exponent. So 5 was our old exponent, and then subtract 1. So when we kind of simplify that out, we get 5t to the 4th as our final answer. And so this final answer is the derivative of t to the 5th with respect to the variable t.
I did this in high school.
Good.
It,
If you're a
I
little bit
I
right,
realized
we're going to keep going through it. There's a question in the chat as well. Will we ever have to find antiderivatives in physics? Absolutely, yes, for sure. And I'll go through how to do that. Hopefully we'll have time today. If not, we'll pick up here tomorrow. Well, not here, but wherever we finish tomorrow. And another comment, that's integration, right? Yes, integration is the same thing as antiderivative. Question in the chat, wait, why can you assume that the coefficient is 1? Just because 1 times a variable is the same thing as just the variable, right? 1 times 2 is the same thing as 2. 1 times t is the same thing as t. And so just so that I could illustrate the point that we're multiplying a coefficient by an exponent, I expressly wrote out the 1 there. A lot of the time there will already be a coefficient there, and so you don't need to worry about the 1. Like in this case. Okay, so here we're going to take the derivative of this expression, 3x squared. But this time, if you look at our problem statement, the variable that we're interested in is now x instead of t. That's convenient because the only variable in this problem is x anyway. So that's awesome. Okay. But we apply the same rule, right? We multiply the coefficient, which in this case is 3, times the exponent, which is 2. And then we subtract 1 from the exponent, so 2 minus 1. Right, so when we simplify that out, 3 times 2 is 6. The x stays there. And then the exponent 2 minus 1 is 1. So x to the 1 is the same thing as just x. So our final answer here is 6x. Okay.
that d over dt and sometimes dx is like throwing me off. It really is throwing me off.
Yeah, you're going to have to get used to it probably because that's just one of the ways that you can do the derivative of. Now, there are alternative notations for that as well, and I'll show you examples of that in just a minute. But this one is the most common one that you will see, at least at FIT. I can't speak for other colleges, but this is the one that's most commonly used in physics. Well, throughout all levels of physics at FIT.
Okay, so whenever I see d over d times variable, it's asking for the derivative.
Yes.
Ah, okay.
I know you had mentioned before that the notation you see a lot is like the prime, the apostrophe.
Yeah, like y prime or y apostrophe or y like quotation mark or apostrophe. I'm
And
not sure how to do it.
I'll show an example of that in just a minute. It means the same thing, the derivative of. Okay. So yes, there's a comment. I used dy dx when you were in high school. Yeah, absolutely. If your expression is written out as like y equals 3x squared, then you can just say dy dx. Right, that's a derivative of y with respect to x. Yeah.
My
So here,
my high school calculus tutor would be so proud of me right now.
oh, good. Okay, last example, I think, for this one. dt, so the derivative with respect to t of 15. Now you can see we don't actually have a t in that expression. It's just a constant. It's just 15. There's no t anywhere. So the exponent on t, which doesn't exist in the problem, is 0, right? Because there's no t. So we do 0 times 15, the coefficient times the exponent, and that gives us an answer of 0. So the key thing to notice here, and this is true for any constant, is that the derivative of a constant is 0. If you take notes, not something to like write down, put stars next to it, highlighted in all pretty colors, that is a true statement that you're going to use a lot. The derivative of a constant is 0.
May I explain why when a derivative of a constant is
Think our internet's acting up again.
Am I back now?
Yes.
Okay,
yes, you are.
cool. Thank you for your patience with this, guys. I don't really know what's happening, but we're
May
back.
I explain why a derivative of a constant is 0?
Sure.
Okay. It's 0 because basically there's, you see like the 6x right there.
Mm-hmm.
Okay, when you don't have like a variable there, it just becomes 0.
Yeah.
Did I explain that well? That's how I try to just,
Yeah,
that's how I like memorized it and stuff.
exactly. If there's no variable, then the derivative is 0. Yes.
Yeah.
So we can
And
take
whenever,
the derivative. Yeah, go ahead.
and whenever if you minus 1 from that exponent, like 6x, that x would become, that exponent for that x would be 0 and it'd be just 6.
Yeah, absolutely. So we can take a derivative of different variables too. And that, like I said, that initial, I call it a fraction. It's not really a fraction because we're not really dividing technically. But that initial notation tells you which variable to use. And then we'll treat the other variables like constants. So if you look at those 3 examples that we've gone through, there's only one variable in that expression that we're supposed to take the derivative of. That will not always be the case. So for example, here we have this expression xt to the 4th. Okay, now we have 2 variables. And if we're supposed to take the derivative of that, we need to be very careful. Pay attention to what variable you are supposed to take the derivative with respect to. Right, so this initial notation, d dt, tells us to take the derivative with respect to t. We don't care about x. So we're going to treat x like a constant, like any other number, like a coefficient, if you will. Right, so if we're taking the derivative with respect to t, then x kind of becomes our coefficient. So we'll take 4 times the coefficient x, even though it's a variable. And then we subtract 1 from our exponent that's on t, our variable of interest. So the derivative of this with respect to t becomes 4xt cubed. Okay, so this would be sort of like a partial derivative. We're taking the derivative of just a part of this, like with respect to one particular variable and not the others.
Ms. Zamora,
Yes.
I feel like I would be a little bit confused. Like, can you go over it again?
Yes. So basically, like if we look at our notation here, that fraction out in front, the d over dt, that tells us the variable that we are interested in, right? So in this case, it's just t. So anything else, any other variable, we'll just imagine that it's a coefficient. It is not something that we are taking a derivative with respect to. And so we'll treat it as just a coefficient. Okay, so in that case, when we apply that power rule of multiply the coefficient by the exponent and subtract 1 from the exponent, then we get 4, our exponent, times the coefficient, x. And then we subtract 1 from our interesting variable, t. So t to the 4 minus 1 is this t to the 3. And our coefficient becomes 4x. Okay, if we wanted to, or if we were asked to, we could do the derivative with respect to x instead of with respect to t. And in that case, we treat
Then t would become the
4.
coefficient.
Yeah, t to the 4th would be our coefficient. And we would take the derivative of just that x portion, which would be, you know, the same power rule would apply. So you'd multiply the coefficient t to the 4th times the exponent, which is an implied 1. So then our coefficient would be t to the 4th times x to the 1 minus 1 is x to the 0. So our final answer in that case would just be t to the 4th. Victor, I see you have your hand raised.
I have a question, but I'm not sure how relevant it is to this. If it's not, we can go, or we don't have to answer. But if for the last example at the bottom where it's d over dt, would the answer be different if it were dx over dt?
Possibly.
It's implicit differentiation, isn't it?
Yeah, so you would have to kind of like state explicitly what x is, like what that would be an equation, x equals something. So in that case, it'd be like x equals xt to the 4th, which in itself doesn't really, like, you can simplify that. And so anyway, I don't know if that answered your question.
Thank you, nevertheless.
Okay. Well, we'll go through some more examples and maybe you'll see your answer to your question as we go through this. Okay. Okay.
Okay.
So
That's why you need the d over dt, because it like tells you what's your variable and what's not.
exactly. Yeah, we need some kind of notation to show us what we need to take the derivative with respect to. Okay. So here, if y is our function, so y equals mx plus b, for example, then here's that notation that you like to use. Y prime or y apostrophe is another symbol, another notation that we can use to tell us to take the derivative. And here it's telling us to take the derivative of that function y. Okay, Now, usually, if there's multiple variables, you would see in parentheses next to that what variable it is that you're taking it with respect to. So in this case, it might be like y prime parentheses x. That would tell us to take the derivative with respect to x. Okay, just another notation that you might see. So the power rule that we've been talking about, one second, is a very important rule and very powerful rule. But there are a lot of other rules that you'll spend an entire semester of calculus learning. And in just a second, I'm going to go through some of those other key ones. But yes, there's another question / comment.
Oh, wait, so the example that you stated before where y prime parentheses x, x would be the constant?
No, x would be the variable that we are taking the derivative with respect to. So like if we look here at d over dt, that tells us the t tells us what we're taking the derivative with respect to. So if we saw, and I think I probably have it later on in a slide, if we see a variable in parentheses, that tells us, hey, this variable is our important variable. This variable is the one that we are taking the derivative with respect to.
Okay.
Okay. Okay. So let's quick run through some of these other rules that we'll apply later on. Okay, so there's a sum rule. If you have an equation that has addition in it, so like f plus g, the derivative of f plus g is f prime plus g prime, or the derivative of f plus the derivative of g. So here's an example of this, right? If our equation is y equals x squared plus x cubed, then the derivative of y, that equation, with respect to x, right? There's our important variable in the bottom there. We just apply that power rule to each part separately, and then we can add them back together. So again, that power rule, we multiply the coefficient by the exponent and subtract 1 from the exponent. So the derivative of x squared becomes 2x, right? 2 times 1 times x to the 2 minus 1 is 1. So we get 2x. Okay, same thing for x cubed. Apply the power rule. So you multiply the coefficient by the exponent 3, subtract 1 from the exponent to get 2. And so that portion of the final answer is 3x squared.
That was real cringe.
She's back.
Hello, am I back?
Yeah.
Okay, cool. Let me get this up again. Okay, and we're back. The difference rule is basically the same as the sum rule, except we're subtracting. So if we have an equation that's something minus something else, then we just take the derivative of each portion separately and then put them together. Yes, I appreciate these jokes, even though I cannot see them. Anyway, here's an example, right? We have d dv. So this time we're taking derivative with respect to v. That's our interesting variable. And here is our equation, v cubed minus v to the 4th. So apply the power rule to each of those chunks individually. V cubed becomes 3v squared. The derivative of v to the 4th is 4v cubed. And then put them back together. And there you have it. That's your derivative of your expression. Okay, sorry. Looking at the chat. Okay, so if we have what are called higher order derivatives, that just means we can take a derivative of a derivative of a derivative as many times as we're asked. Okay, so here's our example. Our function is 5x cubed minus 3x squared plus 10x minus 5. If we want to take the derivative of that with respect to x, first of all, you can see x is the only variable that we have in this problem, but it's explicitly stated here in this notation. The function f, this prime means the derivative of, and the parentheses x tells us take the derivative of f with respect to x. So we can apply these sum and difference rules as well as the power rule that we've been using to do that. So this chunk, the derivative of 5x cubed, multiply the coefficient by the exponent, 5 times 3, get 15. Subtract 1 from the exponent, 3 minus 1 is 2. So that's the derivative of that first chunk, 15x squared. Moving on to the next one, 3x squared. The derivative of that is 6x because 3 times 2 is 6. 2 minus 1 is 1. So x to the 1, same thing as x. 10x becomes 10 when we take the derivative, right? Because x to the 1, if we subtract 1 from that exponent, we get x to the 0. Anything to the 0th power is 1. So 10 times 1 is 10. And then at the end here, we just have a constant. There's no x associated with 5. The derivative of a constant is 0, so we don't even include it in our final answer. Now, this would be taking our first derivative. And you can tell that really easily in this notation because there's only one apostrophe next to the function. Now, if we were asked to, we could take the second derivative, which is the derivative of that derivative. And so in this notation, you'd see a second apostrophe next to it. That tells you take the second derivative, the derivative of the first derivative, again, with respect to x. So here's another way that we could write that out. The derivative, the prime, remember means derivative, of the derivative of f with respect to x. And so we do the same thing that we did before, right? Apply the power rule. 15 times 2 is 30. And then x to the 2 minus 1 is x to the 1. Here, the derivative of 6x would be 6. 10 is a constant, so the derivative of a constant is 0. That part will go away. Yeah, comment in the chat. It's like, ooh, where'd it go? It's like finding acceleration where it's the second derivative of position. Yes, it is. Wow. It's like the things that I'm trying to teach you are relevant. Oh my gosh, crazy. Yeah. So the derivative of a constant will always be 0, right? Yes, absolutely it will be. Remember that, cement that into your brain. The derivative of a constant is 0, always and forever. Woohoo. Okay. So if we wanted to, we could take the derivative of the second derivative, the third derivative, right? And in that case, we're left with just 30 after we take the power rule. So you can see each time we take the derivative, the equation in this case is getting simpler and simpler because we're like eliminating chunks of the expression, right? The fourth derivative then, after 3 apostrophes, we just write the number in parentheses as not really an exponent, but like up there, a superscript, I guess, just because that would be annoying to have to count out 4 apostrophes or like more than that. So anyway, this is how we would write the fourth derivative. And in that case, it's just 0 because, let me hear it from the back, the derivative of a constant is 0, right? Okay.
Oh, weren't there different names for the derivative of the derivative of the derivative of displacement, like velocity, acceleration, and then snap, crackle, and pop?
Yes, there's like the jerk first and then snap, crackle, pop. Yeah. I mean, we don't really ever encounter that in physics. It's just kind of a fun thing to know. Like scientists are really weird in the way that we name things. So that's just kind of fun to know. Okay. Now there are other rules that I would love to talk to you about, but I know we're already at 4:30. Unfortunately, my internet kind of wasted a lot of time for us today.
Are we gonna continue the second part on the next day?
I will, yeah, I'll keep going from here tomorrow. But there's a question in the chat that I want to just quickly address. How do we know the difference between a higher derivative versus a regular exponent? That's a great question. You're going to look at context and also just the fact that like typically exponents are not written in parentheses if it's just a number. And in this case, like we're taking the derivative because the fourth derivative, because we see this 4 appears in parentheses. Whereas if you were just writing an exponent, like something to the fourth, like up here, this 4 does not need to be in parentheses. So the parentheses will likely not be included. But your best clue to that would probably just be context. Okay, any other questions, comments, or concerns about this part? All right.
Pretty good.
My internet connection being what it was today, I'm not exactly sure how this video is going to like piece together. If it comes out super just jumbled and not good at all, then I'll just post a link to a previous year's recording of this lesson, although it will go beyond what we talked about today. But I mean, we'll see how it turns out. Maybe it'll be this one. Maybe you'll see a link to a different one. Either way, hopefully my internet will be better tomorrow, and I hope you guys have a great rest of your day, and I'll see you then.
Is there an actual hurricane going on outside?